Okay, hello, my name is Ovchenko Grigory. I'm from Team Ukraine, and now I'm going to report the solution of problem 3, paper tube. According to the statement of the problem, we have to investigate the rolling over of the paper tube and define what determines the period of the jerks, depending on different parameters of the problem. Here you can see the demonstration of the effect. As you can see, the paper tube rolls with time, and the angle of the rolling increases. Also increases the decreases the curvature of the paper tube, and so the period of the jerks decreases with time. In our problem, here you can see the structure of our report. In our problem, we will first of all qualitatively investigate the effect. We will demonstrate it and find out the dependence of the non-elastic deformation of the paper. Then in theoretical part, we will investigate the equations of equilibrium and investigate the conditions of the unwind and unwinding time. Then we will investigate the influence on main parameters on the problem and compare this with the theory. Let's start from the preliminary investigations. First of all, let's consider the paper itself. Paper consists of fibers, and depending on the external tension applied to the paper, if the deformations is small, then the fibers still be entangled. As we decrease the external tension system comes to its initial position. But if fiber is unentangled, then the paper do not return to its initial position. In our solution, we will use such an experimental setup. We will use paper, which is rolled. This paper pushes on a base, which pushes on to the electronic wire. And using this wire, we could find the torque of the paper itself. Here you can see the dependence of bending torque depending on the curvature of the paper as we rolled paper over. And you can see that this curvature increases, and we approximated this dependence, so we used it further. But as we try to decrease the external torque, we saw that the curvature do not comes to its initial point, and thus we see that this dependence is hysteresis, that we observe hysteresis in our problem, and thus this bending is not linear. And also we did the same for different initial position of the curvature, and you can see that the paper returns to the different points. Also, we saw that as we bend a paper tube and rest it for some time, the bending torque increases with time. And it is a main effect in our problem that after some time, the torque is higher, and thus the paper is rolling over due to this effect. Using this dependence, we can now qualitatively explain all the stages of the curve. You can see that as we try to apply external torque, the curvature increases, but as we try to decrease it, the curvature decreases, but after some time, bending torque increases due to the relaxation effects in our problem. So now we are able to qualitatively explain this effect. For this, let's consider a small part of paper and forces acting on it. As the paper rolls over, the internal forces increase, and after they are higher than the surface reaction force, the slip appears, and thus the paper moves. After some time, paper comes to its equilibrium position, and this effect continues periodically. Now let's move on to the theoretical investigation of this effect. To do this, we introduce such geometry. We use polar coordinates, using which we define the curvature of the paper, and we consider forces acting on it. We consider internal forces to have a tangential and normal projection, and also we consider external forces acting in our system. And we write down the equation of balance of forces and balance of torques in our system, using which we get the final set of equations for the equilibrium position. And now let's discuss what happens when the slipping occurs. The slipping occurs when the external force is higher than the friction force. And if it happens, we in our simulation write the second Newton's law for the motion of the elementary fragment, where we add the internal forces and external force, which is related to the drag friction. We simulated this motion in the MATLAB, and here you can see the result of the simulation. We see periodical unwind of the paper tube, but in this period decreases with time. Here you can see the dependence of radial deflection of chosen point on a paper tube with time. You see that it increases, it saturates, but there are periodical unwinds, which period indeed increases with time. The same dependence for the angle, which decreases with time. And we compared this dependence in our experiment. We investigated how the angle of a farthest point on a paper tube depends on time, and compared it with the theoretical prediction. And you can see that our theory really good predicts initial stage, but on the final stage there is some kind of problem which is related to that the surface isn't uniform, and thus the friction coefficient may be different in different points, and thus as our theory predicted disruption, it didn't happen in the reality. Now let's move on to the investigation of influence of different parameters. We first of all started from the investigation of friction coefficient, which we measured for different bodies which we used. And here you can see the dependence of time between disruptions as a function of time, which we found both theoretically and experimentally. Indeed, we can see that they really good correlate even for higher times. As a dependence for number of disruptions on initial radius, we can see that it decreases, which is also logically because of, in this case, the curvature is lower. And we investigated the number of disruptions on the length of the paper. We can see that it increases, but there is a problem for higher length of the paper, which is related to that the leads to the different radius of curvature of different points of the paper. So in our problem, we first of all qualitatively and quantitatively investigated the different properties of the paper. Based on these experiments, we explained the whole propagation of the whole behavior of the system, and built our own theoretical model, which describes this process. Using this model, we investigated the dependence of different parameters of the system on initial radius, length of the paper, and other main parameters of our problem. Thank you for your time.
So first, thank you for your presentation about this problem. I thought that it was very clear, and I appreciated it a lot. So first, what I liked is that you were able to simulate the whole spiral of the paper, and not only a cylinder of paper, which is something that personally we couldn't do. And you also were able to study a lot of parameters, and you showed these parameters that you studied on the variation of the paper, which was pretty interesting and confirmed your model worked well. And also you had this approach with bending torque, which I found was relevant. I had a few problems. Particularly, I didn't understand how you measured the deformation of paper and the final angle, but I think that you will be able to explain it without problems. And also, I didn't see any check to see whether the jerks were only uncertainties of measurements. So about the question, I have obviously how you checked the angle of deformation of the paper. Also, because paper is an anisotropic material, and I don't think I heard in your presentation that you studied this part, and also other parameters such as the type of paper, which has influence on the friction coefficients. I also had a question about how you only studied the friction of the floor on the paper and not maybe other mechanisms such as friction of paper over itself or friction or maybe another mechanism as friction. And also I wasn't able to see for how much time you made your experiments. And it is an open question. I would like to know how you think your model would work over an extended period of time. So that's it for my questions. I would be happy to discuss now.
Okay. You can start the discussion. You have 5 minutes.
Okay, yes, let's start from the first one about the angle. I have to explain that if we have a paper tube, we measured the angle of the rotation of the point which is at the edge of the paper tube.
Okay, so
It's the farthest point, yes.
You plotted the trajectory of the extremal point.
Yes,
and,
yes.
Okay. Oh, we did the same method. Okay, I didn't get it. And so about the variations on paper, did you try having stripes of paper in one direction of the paper or in another?
Yes, mainly in our experiments, as we showed the dependencies of bending parameters of the paper, we investigated it only in one direction of the bending. But yes, we also understand that paper is anisotropic material, and thus the whole effect may depend on different directions. Mainly in our experiments, we used we cutted the pieces from along one direction, and using the same papers from the same pack.
Okay, and do you think that with a paper that is isotropic, such as I think glass paper, do you think it would change the results of the experiment?
The anisotropy would change.
No. So it's about my other questions, which was about how you chose only to study the friction of the floor on the paper.
Yes, we investigated only friction with the floor. Yeah.
Okay, and do you have an argument that would justify only studying this friction?
We have to take into account the friction of paper on itself only in a case when paper is rolled only at the first stage. The first stage has a small time period because of paper really quickly unwinds to the thickness to be enough not to have a friction between the different layers, and thus mainly further further behavior depends only on the friction with the floor.
Okay, but for example, do you think that if you had a strip of paper that was suspended in the air without friction, we would see jerks? So in your model, we wouldn't see any because there wouldn't be any friction, but do you think this is the case? Or did you do this experiment?
Yes, in the air there is some kind of other experiment because of one layer falls down on another one, and thus the friction between layers would be observed in each case. In our situation, it is horizontal geometry, and thus we during the main period of the whole effect, we do not observe friction of layers themselves.
So in your case, you're talking about a roll of paper that would be, I don't know if you can see my camera. So in this sense, but if it was vertical, it wouldn't friction at itself?
It would friction. If we suspend it vertically, in our experiments, it was in this direction, but if we suspend it in this one, yes, we will observe jerks because of the friction of the layers, one with another, yes.
Okay. And so my question about the duration of the experiment, how long did you follow this evolution of paper?
Nearly 2 minutes, but to get our points, we made different experiments. We used nearly five paper tubes, and we somehow found the statistics, and thus by averaging we put it points on our plots.
Okay, so you didn't go further than 2 minutes,
Yes, mainly in
but-
our experience, yes.
but did you see jerks after this time step?
After not in all cases, like it wasn't very frequently after these 2 minutes to occur for a jerk.
Okay, and did you
Okay, from this moment
change-
on, the other team members can join the fight. Just let me remind you that if you want, you can still share your screen to help your presentation, and you can also use the Blackboard
Okay.
if you want to write on them. Okay.
do you try to change tubes of paper between your experiments? Because as you explained at first, so the paper can have inelastic deformations, so because of high hysteresis. So did you use a new paper in every experiment?
Yes, in each experiment we use a new stripe, yeah.
Okay, and did you try to use the same stripe and see whether at some point it would behave differently?
Yes, it behaves differently indeed, and because of this, because of the as the elastic properties depends on the prehistory of the paper tube, we didn't use the same paper tube in our experiments for a long time. Yes.
I have a question. So I'd like to ask, how did you roll the paper to ensure that you can always roll it in the correct way? Is there a method or anything that you used?
Method of rolling.
Yeah.
We roll the paper on a tube. We show the plastic tube around which we roll the paper. And as we roll the paper, the other side remains unrolled. It remains straight. Like we are
Okay.
held in and we roll something like this.
Okay. And do you think if you change the tube that you use to roll, would it be different? For example, if you use a pen that's not very round, then would it change the results of the experiment?
Yes, of course, because if we're rolling around the pen, not round pen, there are corners at which the curvature is much higher, and this leads to the hysteresis effects at this point to be much more variable.
I see. Okay. Thank you.
So you had a model, if I understood correctly, you had a model that predicted the time at which every jerk happened, right?
Yeah.
And do you think this model, and you said that after 2 minutes, you don't see much jerks happening?
Yeah.
And you think this model still holds up after those minutes, or does it hold up like to time equals plus infinity?
Yes, you're asking about experiment or theoretical model?
Since you said the experiment basically stops after 2 minutes, does the model hold up after that?
Yes, like our theory is applicable for each time, and our theory, we stopped our simulation at the point when the angle doesn't strongly change. There is no additional wind. In the experiment, as I mentioned, it's 2 minutes, and yes, in some cases, it may be observed that after these 2 minutes, the additional jerk may be observed, but in most cases, we didn't see that.
Okay.
Also about your model, could you precise the parameters that you had to fit to make your model look like the experiment? At what parameters you had from physical measurements? For example, I suppose that you knew the static friction coefficient, but you maybe had to find the bending moment of your paper.
Bending torque we have found from the experiment. This dependence, yes, we have to find this dependence as which we explained before. Also, we have to find not only the static friction coefficient, also the dynamic one, because it defines the dynamics of the motion of the system, and some usual parameters such as the surface density of the mass of the paper and something like this, yeah.
I think we don't have any more questions. Thank you.
Maybe you have some problems that you would like to discuss if you wanted to improve on the experiments. So what would so if you didn't finish the experiment, what would be the other measurements that you would have done?
That we haven't done.
Excuse me?
The measurements that we haven't done. Or, I'm sorry.
No, my question is, what other measurements would you like to do if you had more time to study the system?
Like maybe to define the number of unwins more correctly, like with higher accuracy, but there's no principal difference between the 20 and 21 unwin. Like it's.
Yeah, I have a question to the reporting team. Did you bother about the center of mass of the piece of paper, how it moves horizontally, if it ever moves horizontally, because it describes the fluctuations of the friction force. If it's always the same, I would expect the center of mass not moving horizontally. If there are some fluctuations of the frictional frictional force, then probably you can see some random motions of the center of mass of the piece of paper. So did you ever consider this? Did you pay attention to that?
In the theory or in an experiment?
Experimentally, yes. Because
yes, okay. We understand that indeed center of mass may move only due to the external friction forces. Indeed, if the paper moves, then the friction forces at each point are nearly the same because of it's just a dynamical friction. And if the paper is winded symmetrically, their center of mass doesn't move, but mainly we understand that it moves something like indeed randomly because of paper and winds, and that's a different number of winds are opened. I will say it so, and thus center of mass moves in one direction and in another, and moves something like circularly, and it is only if the surface is uniform. In the case of ununiform surface, in different directions, the friction force are different, and thus center of mass would move in one direction. Yes, that's all.
Thank you.
Thank you very much for your answer. More questions from the jury?
Well, I had my hand raised. I don't know, may I ask a question?
Yeah, here we go.
I would like to ask about this main phenomenon of the problem. In the very beginning, you attach the paper, you roll the paper, you attach it to the torque, and then you measure the weight it is exerting, or the force it is exerting on the weight. And then you see the change with time. And I am not familiar with this kind of physics with the paper. I wonder what kind of microscopic phenomenon is that? Why this torque is changing with time?
We think that it is related to the inner processes. It's fibers bending between them, because of as we fast increase the external torque, the fibers move in some unstable condition, but after some time they accept their more their best position, and it leads to the increase of the torque.
Is it some well-known thing discussed in the literature? Have you looked at the literature?
Yes, indeed.
Okay. Cool. Thank you.
May I also ask a question?
Sure.
I wonder, is there a dependence of number of jacks on time at which the piece of paper stays in bend position? you can leave it in bend position for an hour, for a minute, or maybe for a month. Do you investigate this dependence?
Dependence of number of jerks with time?
With time in which this piece of paper was bent.
Yes, we investigated it in our presentation. May I open the demonstration of the screen? Yes, it is nearly here. Yes, it's dependence of number of disruption on time, time between disruptions, and thus we can define the number of disruptions in time.
It's time not between jacks, but it's time, it may be a very long time. For example, it may be several hours.
Yes.
When you keep this piece of paper in bent position.
Yes, yes, it remains bended. Yes, it's true.
So only 40 seconds. And what about, to say, 40 hours?
We didn't observe any jerks after these 30 seconds in this experiment.
Okay.
The paper just stayed bended for a long time, yes.
What do you expect for different thickness of paper, like 80 grams per square meter or 120 grams per square meter or something like this?
Okay, we expect that for higher thickness, there will be a higher mass of the paper itself. And thus it will lead to the different, let's say, different friction force with the surface, because the mass is increased and thus the normal reaction force also increased. And also for higher thickness, it indeed maybe observes the effect of the internal friction between layers. I hope for the papers that we investigated, we didn't have to take into account. But for higher, it may somehow change the behavior of the system.